Welcome back to Advent of Code 2023, day 20, final stretch. Slowly making our way back to the beginning of the island where the trebuchet was. Well, okay, look, they've put some gaps here, so I'm guessing it's going to be 21, then 22, 23, 24, 25. So we'll finish here. I guess this is where the trebuchet was. That's cool. So is the music playing? Yeah. All right then, day 20. Pulse propagation. Just have a quick. I was gonna say it looks like assembly code, but I guess not. But it is some sort of scripting, custom scripting code. All right. With your help, the elves managed to find the right parts and fix all of the machines. Now they just need to send the command to boot up the machines and get the sand flowing again. The machines are far apart and wired together with long cables. The cables don't connect to the machines directly, but rather to the communication modules attached to the machines that perform various initialization tasks and also act as communication relays. Modules communicate using pulses. Each pulse is either a high pulse or a low pulse. When a module sends a pulse, it sends that type of pulse to each module in its list of destination modules. Okay. There are several different types of modules. Flip-flop modules, prefix percent symbol, are either on or off. They're initially off. If a flip-flop module receives a high pulse, nothing happens. If it receives a low pulse, it flips. Okay. This is like I'm back in school learning electronics GCSE. Flip-flops, D-type flip-flops. You can have D-type flip-flops which are triggered on low edges and then high edges. Conjunction modules. Remember the type of the most recent pulse received from each of their connected input modules. Prefix ampersand. They initially default to remembering a low pulse for each input. When a pulse is received, the conjunction module first updates its memory for that input. Then, if it remembers high pulses for all inputs, it sends a low pulse. Otherwise, it sends a high pulse. Okay. From each of their connected input modules, so they have multiple connections. So when you get a pulse, it changes your memory to high. Oh, I get it. Okay, fine. That way, time doesn't matter. Like, you can then send the high on a different input and so on until it gets highs all along. And you can disable it by sending a low, and then it will remember low there. So I get it, sort of. And it's basically an AND gate, sort of, but with memory. So you could think of it as a latched AND gate. You could have latches on each of the inputs. It's not AND gate, it's NAND gate, isn't it? Once all the inputs are high, then it sends low. So it's basically one big NAND gate. Alright, there is a single broadcast module named Broadcaster. When it receives a pulse, it sends the same pulse to all of its destination modules. Alright, I'm thinking about how I can code this. Yeah, okay. After pushing the button, you must wait until all pulses have been delivered and fully handled before pushing it again. Never push the button if modules are still processing pulses. Sure. Okay. Pulses are always processed in the order they are sent. So if a pulse is sent to modules A, B, and C, then module A processes its pulse and sends more pulses. Hang on. This sentence is important. So if a pulse is sent to modules A, B, and C, then module A processes its pulse and sends more pulses. The pulses sent to modules B and C would have to be handled first. Okay. So it's we want to use a queue, not a stack, essentially. Or like a FIFO queue. FIFO queue, yeah. Alright, the module configuration lists each module. The name of the module is preceded by a symbol identifying its type, if any. The name is then followed by an arrow and a list of its destination modules. For example, right. It says broadcaster. And then we got these, and then we got this. Alright. Probably want to create a class. Conjunctions. Do I want to create a class for each type? We don't want to do any kind of like subclasses and stuff. Let's not worry about that. Just create a separate class for I suppose we could. I forget how to do that in Python. You would need, so you want to, we could just do if else's. If my type is this, do this, otherwise do this. Yeah, straightforward enough. Alright, in this module configuration, the broadcaster has 3 destination modules named A, B, and C. Each of these modules is a flip-flop module. A outputs to B, which outputs to C, which outputs to another module named inv. Inv is a conjunction module, as indicated by the at prefix, which, because it has only one input, acts like an inverter. So the NAND gates have got to keep track of how many inputs they actually have. The flip-flops don't care, do they? Wait, flip-flop has how many inputs? I guess it can have an arbitrary number of inputs and an arbitrary number of outputs. It doesn't matter. The flip-flop will still work. It will just send a low pulse to all its out. Okay. So flip-flop doesn't care about its inputs. We don't need to record them because we'll just get the pulse. But conjunctions do care. So we might need to... Alright. Fine. By pushing the button once, the following pulses are sent. So pressing the button does what exactly? Sends a high? No, when you push the button, a low pulse is sent to the broadcaster. Okay. And the broadcaster, when it receives a pulse, regardless of whether it's low and high, it sends it to the others. All right. Is there only one broadcaster? There is a single broadcast module. Okay, got it. So when you push the button once, it sends a low. So the broadcaster. The broadcaster sends low to A, B, and C in that order. Then you have A, and so you're gonna have to have a queue of these pulses. A sends a high to B. Then the next is off the queue is B sends a high to C. C sends a high to inv. Inv sends a low to A because it's all of those are high. It's all of its inputs, of which there's just one. It's high. So it sends pulse to A. A sends. All right. So these can go in cycles. So you could create a situation which in theory goes. I mean, it's not like a Turing complete system, is it, or anything like that? But you could create a system which, like I don't know, a binary counter, which could take many steps before they're all high or something like that. Well, can you make a binary counter? You can, but that's what flip flops are for. But you need delayed. You need some sort of delay. Anyway, more interesting example. 2 flip flops. Multi-input conjunction. Yeah, okay. I don't need to read the examples. I get how the individual modules work. Alright, so in the first example... Wait, so... To get the cables warmed up, the elves have pushed the button 1,000 times. How many pulses got sent as a result? So we're counting how big the queue... Well, or how many items get entered into the queue, aren't we? This is interesting. In the first example, the same thing happens every time the button is pushed. So after pushing the button 1,000 times, 8,000 low pulses and 4,000 high pulses are sent. Oh, okay. Thank goodness the numbers aren't that big. It's that big, and then you're multiplying them together to get that. Okay. I was thinking if it's that big, that's a bit worrying, because that's too many. Millions. And the input will be bigger. But if it's only 1,000, that's doable. Just by simulating the whole thing. I was worried that we might need to find shortcuts or find loops and do LCM again. I mean, that might be what we have to do though, so in part 2, I don't know. Here we got that many pulses. Yeah, we can deal with that. Okay. Determine the number of low pulses and high pulses. Alright. And that's the system. Part 2, I'm worried about part 2. We could have some big numbers for part 2, which... Oh, hello, DJ. I didn't get your message. How long ago was that? Alright, so... Interesting. Okay. This part 1 at least is just a plain simulation, so let's just do that. Alright, so Python 20, 20. Those are the instructions. Okay, so we need... So there's 3 types of modules, okay. D-type. I'm calling it D-type. It's not a D-type, it's a flip-flop. Flip-flop doesn't really care about how many inputs it has, does it? Okay. 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 So I would say let's just make a list of modules. Should we just okay, first let's do this. Module table. First, before we try to process these, we just want to create all these modules so that we're able to actually... Okay, tell you what, let's do a first pass through the input. Just read all the modules, just put them into our table. Then on the second pass we can start mapping these, because otherwise it's just... If you try to do both in one, then... Like, I'll try to access DM, but DM doesn't exist because I didn't create DM. So, okay, so on the first pass, this is the first time I've actually read the input twice, but that makes sense to do that, so... Right, and it's not like we can have CG percent, oops, and CG ampersand, is it? I assume these names are unique. Yeah, they must be. Okay. So, first, let's just do... Okay, so just left, right equals... Alright. Left, right equals line dot strip dot split. Let's split on the this big chunk here. Alright, so the left is just that, so okay. So left. So okay. Let's create a class called module then. I don't think we should be calling it module. Is that okay in Python? I guess it is. Module's not reserved. Okay. Shall I just we've been using data class with some success, so but we don't want... Yeah, okay. So let's keep using data class. I like it. So it's gonna have name, which is a string. What else? So we need inputs, which is a list, but only... Well, okay, we're going to need a type. Are we allowed to use the word type? That can be a string. Inputs. will be a list, and outputs will be a list. Okay, so inputs is not needed. We don't use inputs if it's broadcast or flip-flop. I'm not gonna do like subclasses and a class hierarchy. It will just do the basic one class module. It doesn't if else to do each piece of logic depending on what type it is. All right, so that's a module. All right, so we want to just create all the modules. All right. So can something pass a signal to itself? They didn't forbid it, did they? Should I just code it in case that can happen? Let's see. Nothing technically forbids it, so whether or not the input does that, let's just code it to account for that. I mean, you could have an NAND gate which passes something into itself, I don't know. So in that case, we want for M in, so we want basically the left, so the module that we see on the left is going to be just left, but ignore the first character. And then we want to concatenate this list with just this comma separated. So it's going to be right dot split comma space. That returns a list, right? For each of these, okay, so if module table, so if m not in module table, we're gonna add it, equals module, so the name is gonna be m, and then all the other, the type oh, we don't know the type. Okay. This is actually way easier then. Okay, discard right because we don't know. We don't care about right. So yeah, this makes more sense because you get the left side covers every possible module. Pretty sure that's how they've defined it, so we don't need to create modules from the right pieces. Those are just pointing to ones that are defined in the left. Alright, so first pass, we just define all the modules. So, type, module type. If left dot starts with percent, then just create a So it's going to be left, 1 onwards. Module. Alright, so the name is this. Does a module need to know its name? It's in the list, I don't think. I don't think we do. Okay, we don't need to know its name, because its name is referenced from outside. Okay, so it just needs to know its type. So the type is going to be... In this case, it's going to be flip-flop. And the inputs are going to be... So a flip-flop doesn't care what its inputs are, right? So we can just leave it as none, because we don't need to process it. Outputs is a list. It doesn't like... Alright, fine. Put an empty list. It doesn't like none type. Alright, so, okay. Similarly, if it starts with ampersand, so we do what was it called? Conjunction. And then this one, it's going to be left, but we know it's going to be called broadcaster, aren't we? So we should probably just say, doesn't matter, we'll just use left. Broadcaster. Okay. Okay, now do this again. But now we have all the modules defined. So for each instance, which is existing in our table, one unique instance per module, named module, we can now okay, so if outputs equals right dot split comma, all right, hello Wogger. Doing some how would I describe it? It's like basic electronics coding. Like, I don't know if you've ever done any form of electronics, but it's like you've got NOT gates, AND gates, OR gates, flip-flops. So it's like a NOT gate. When you send a signal of 1 into it, it outputs 0, and if you put 0 into it, outputs 1. And then you've got AND gates, where it's like, if all the inputs are 1, then it outputs 0, otherwise it outputs 1. I don't know if you've ever covered that area of physics, electronics, but it seems that we are coding kind of a rudimentary system like that, where we have only 2 types of gates. One is the flip-flop, so it outputs it basically flips on and off. So if it was last on, then it goes off, and if it was last off, it goes on. And a conjunction, which is like an AND gate. So it's like it sends a pulse. So it sends a high pulse if. No, it sends a low pulse if all its inputs are high. Otherwise, it sends a high pulse. It's actually a NAND gate. Not really my area. Yeah, it's not like. I studied it in school, but it was an optional course we could take called electronics, but it wasn't covered in basic mandatory physics. Well, at least it might have been, but not to a high degree. But yeah, there was a whole course we did in school called electronics, which was optional, and that's where we studied this stuff. But it's interesting stuff because you can. It's like the most rudimentary form of programming where you're literally just you can make, I don't know, like binary counters. So you're sending a signal, and each time you send the signal, it creates a series of zeros and ones, so it looks like you're counting up from 0 to, I don't know, 16 or something. I mean, it's the building blocks of actual programming, but you couldn't make anything really complex with these gates. But I mean, a microprocessor is basically lots of these gates, thousands of these gates hooked up together. But okay, this puzzle that we have is basically asking us to just use these 3 types of modules, as it calls them, and just hook them all up to each other. So they each have inputs and outputs. And if we send a signal into one, then it continues a signal to certain other ones, and then each of those in turn sends a signal to others, and so on. And we basically have to simulate this. So I'm trying to just create a module for each of these 3 types. So the most basic type is the broadcaster module, which is just the beginning one. So every time you trigger the broadcaster, it just sends a pulse to each of its outputs. Doesn't do any logic, it just sends a pulse. So so we want if left equals, if it just says the word broadcaster, then hang on. Okay, if left says the word broadcast, so we want to know which module is being referenced here. Then M equals, just pull it out of the module table. Else. Actually, okay, there's a cleaner way of writing this. M equals that if that else that. So we're saying that means M is always going to be defined. All right, so and the ID won't complain. So we're saying if the name is just the word broadcaster, which is the special one, then we pull out broadcaster from our table. Otherwise, pull out whatever the name is. Just take off the first character, so FP, QH, MR, and so on. Alright, so that gives us our left-hand module. And so for each of these on the right-hand side, we want to add these modules to its set of outputs. So for output in the right-hand side, we want to say m.outputs.append, and we want to add just add that module to its list of outputs. So it's going to be module table output. All right, so that hooks up all the outputs correctly. What else? All right, the special case. If let dot starts with and, this is the special case because the conjunction module, which is defined by having ampersand at the start, needs to know all its inputs as well, because it does logic. It does conditional logic, but the other types of gates don't. So the conjunction needs to keep track of how many inputs it has and which ones they are. So how do we do this? We say oh no, wait. This has to be done inside this loop. All right, so, okay. Output module equals that. Let's just define that first. Okay, so we put output module in the outputs. And now we look at that output module and we have to put m in its inputs by symmetry. So we have to say, but we only do that if it's a conjunction. So if output module dot type is conjunction, I mean, we could just do it anyway. We don't need to check if it's conjunction. Yeah, let's just do it anyway, even though we might not use those inputs if it's a flip-flop. Maybe it's nice to store them anyway. Okay, so output module dot inputs dot append m. Okay, that's nice and clean. No conditioning. So if I've done this correctly, we should now have now just be able to print module table and it will, I don't know, let's see what it looks like. String object starts with. All right, so for example, CG module type equals flip-flop. Let's check that this is correct. Type equals flip-flop, correct. Inputs empty, outputs empty. Well, that's wrong. CG should have two outputs, FB and RC. This for loop never executes because we reached the end of the file. We have to close the file and open it again. Because I'm just going through the file twice. It's just, the logic is easier that way. Yeah, okay. Key error RX. Huh? Oh no. RX. What the heck is RX? So, okay. RX is a dummy module. It's not even defined, so it has no definition, but it receives pulse. But we don't know what type it is, and it doesn't do any logic because it hasn't got a schematic, so it doesn't appear on the left side anyway here. But nevertheless, it receives a pulse. That's interesting. Why have they done that? We might need to do something with that. RX for part 2. And now we can just ignore it. Because there's no point creating a module for RX if it doesn't do anything. Alright, so let's say if output, so if the string RX is not in our module table, that means we didn't find it in our schematics on the left-hand side definitions, then just skip it. So RX will just never get processed. Okay. It's stuck in an infinite loop? How is that even possible? What? We've not used any while true. These are just for loops, so it should not be possible to get stuck in an infinite loop, surely. Print the line. I want to see what line it's looking at here. So it goes through all those lines, and now it's stuck on this. How could it be stuck? ZC maps to KL. ZC, that's the final line. ZC, KL. Why is it stuck on the final line? What is it doing? Also, why have we got these empty spaces here? Print line. Something isn't right here. Print line. Why is it printing an extra line between these? What's going on here? Have I done something really... Print line. It's printing the line, okay. Oh, okay, I think the extra space is because of the, Oh, let's try that. Oh, it's just because of the new line characters. It's just the way it does it. Okay, that's fine. Fine. Alright, so that's... We don't need to print line. So it gets to the final line. ZC to KL. Then what? What is it doing? Is there something weird that happens if I try to open this text file twice in succession? Because the second time, clearly it's still able to read the lines from the beginning to the end. And it gets all the way to the last one. Try debug? Where does it actually get to? Okay, we'll pause. Where is it? Recursive? Oh my god. I think I know what might be happening. I never thought this could happen. Hang on. I think because modules contain... A module has a list of modules as one of its properties. And those modules, in turn, have lists of modules. And those modules, in turn, have lists of modules as their properties. What it's trying to do is if you print one module, it's actually stuck in an infinite loop because each of those modules has out modules, and each of those modules has modules, and each of those modules has modules. That's one downside of using data class. That can happen. Okay. Let's just say we override the printing mechanism and just print the name of the module. Don't try to print its properties, because this is a recursive... Modules contain modules, so... I've never encountered that situation before, but then this is the first time I've used data class, so I guess that makes sense. You have to be careful of how you use data class. Just say return... Well, we don't know its name. Okay, we're going to store its name. And then we have to store its name when we create it. Module. So it's going to be left one. In this case, it's going to be left one again. And this case, we'll just call it... Just call the broadcaster. Right. There we go. CG, CG, JZ, JZ, and so on. All right. I mean, this... We could actually do a better representation. We could actually print... Oh, we'll think about it. We could actually print a condensed form of its inputs and outputs. But that's not important right now. So yeah, we've got a module table. Okay. So that's the parsing done. And now we've got all the information from this in code form. Still a lot of work to do though. Okay, so we have to code what each of these things is gonna do. So we need one big queue. I could do with some food, but I would have to pop to the supermarket. see if we can get part 1 done. Let's think. So we have a queue. It's gonna have to be a proper queue. So from queue import queue. So we've got the queue equals queue. So this one queue is referenced by all the different modules. They're all, well, put this up here. It's to be defined up here. Okay, so when a module is given a pulse, so the module is given a pulse. That pulse is either 0 or 1, high or low. So let's say that's just the pulse value. And the only other thing we need to know is who sent this pulse. If we are conjunction. If we are flip-flop, we don't care who sent the pulse. And broadcaster, we don't care. Okay, so let's say sender equals none by default, and if it's a conjunction, we'll actually define the sender. Okay. All right, so then we just have to do an if-else on the types. I mean, this is a nice example where you could actually make subclasses. So pulse will be something that will be defined by just different classes. Let's just do just do the easy way. If type, if self. So if I'm a broadcaster, self type is broadcaster. This one's the easy one. Queued. All right, so in this queue, we're gonna have to put a tuple, which is the destination, the value we're sending to that destination, and the sender. Yeah. Okay. So broadcaster. So for output in self.outputs, q.put. So we put the destination, which is just the output, the value. Hang on. So let's read how broadcaster works. This is a lot of coding that we need to do for part 1, but it's not hard, it's just there's a lot of steps we need to do. Broadcast, okay. When it receives a pulse, it sends the same pulse to all of its destination modules. So whatever this pulse is, value, it gives the same value to each of them. and the sender is self. Right, we just send a copy of ourself. Is that? Yeah, we're allowed to do that, right? Yeah, okay. That's not some weird recursive thing. Okay. Elif self.type is flip flop. Flip flop. In this case, for output and self.outputs, okay, so a flip flop, if it receives a high pulse, nothing happens. If it receives a low pulse, it flips between on and off. Well, there's another thing I need to keep track of here. This is why we need to be subclassing, but we can do this. Okay, so we need flip state. Oh, we need some more stuff here. Flip state. This is a Boolean. No, just a int. I don't like using a Boolean for pulse. We could. If it's just low and high, it's not like it's that much more efficient, but it might be cleaner. I don't know. Yeah, okay, let's try using a Boolean. Alright, so flip state bool. So flip state. You know what? I think we have to define init here. Override init. We don't want to use the data classes built in init. It's starting to get to the point that we don't need to use data class, I think. This is very custom. Alright, so given a name, a type, that's it, okay. So self.name equals name, self.type equals type. Module object attribute name is read only. Well, we're initializing it. Alright, you know what, just change that then. Alright. But there should be a way to... Is init and not allowed to... It's read only, but we're not allowed to just... Alright, whatever. It's no longer frozen. I wanted it to be frozen, but I don't know what we were supposed to do there. Alright, so self.inputs equals empty list. Hang on. If type is conjunction no. Self.inputs equals empty list. Self.outputs equals empty list. Self.flip state equals false. It starts low. Is that right? Okay. Starts low. And the other thing we need, I guess, is Shadow's built-in name type. Yeah, it does, doesn't it? We could say module type. Yeah. One more thing. The conjunction needs memory. Okay, this is a good place to use a default dict. Let's say conjunction memory equals default dict. So according to conjunction, you remember low for each input, okay? So bool should default to false, right? We can just say that. This is tricky to code. All right, I think we've got that done now. Okay, back to the logic. All right, so if it's a broadcaster, output and self.outputs, we just broadcast the message to those outputs. Okay, that's straightforward. If it's a flip-flop, for output and self.outputs, okay, so we only do anything if the pulse is high. No, if it's low. If not, value. So if the pulse is low, then we do something. For each output, then our pulse, our flip state is flipped. Okay, so self.flip state equals not self.flip state. Okay. And then we output that new flip state, right? So it says if it was off, it turns on and sends a high. Yeah. So whatever the final flip state is after doing that not, we output that to every output. And yeah, okay. Finally, conjunction. Alright. So if we have conjunction, we're keeping track of what the most recent pulse was from each connected input. So the first thing is default dict for this let's say self.conjunction memory for the sender we always have to send a sender, so let's just send a sender. Sender.name, we just hash the name, don't try hashing the whole module. So equals so we change it to be whatever pulse we're seeing, so equals value. So it defaults to false to begin with. That's why we use the default dict. That's convenient. It just remembers false for every sender that gets accessed. And when we receive a pulse, we update the memory to be that value. Okay. So we do that first. Then we check if all self.conjunction memory dot input module dot name for every input module in self.inputs. So that's saying for all my inputs, if every single one of them has a high value in my conjunction memory table. Yeah, Boolean is useful here. It's just easier to write these phrases. If that happens, then we output a low pulse. Otherwise, we output a high pulse. Okay. Okay. Output pulse. Output value equals not all. Is there another way of phrasing that? Why doesn't it like this? Take that off. There we go. So if it's true, if all of those are true, then we want to output 0, otherwise output 1. Okay. And then we just do the same thing we did before. Output value. Alright, you know what? This can be made better. Just take this outside there. And then here, instead of doing this, we just define output value equals value. Oh wait, no, we can't do this because the flip-flop may not send the pulse. Broadcaster and conjunction will necessarily send a pulse, but flip-flop won't necessarily send the pulse, so that makes it a bit awkward. So okay, we have to keep this within the if condition. So so for output, instead of output's queued up output. So here, this is going to be this output value self. All right. That is one pulse. We put new things on the queue. Okay. Now, what do we do? Just make sure that... Oh yeah, we've defined this differently, so we need to give it a name and a type and nothing else. Okay, is that fine? Okay, good. All right, the actual logic, the actual runtime stuff. All right. So we need, so Q is empty. We want to define press button. So if you press a button, what happens? They said we actually trigger broadcaster. So Q.put. So it's going to be a tuple. We need to know the broadcaster. So broadcaster equals module table broadcaster. Okay. Module table broadcast. Okay, so now we say when pressing the button sends a signal to the broadcaster. And it sends a low pulse. Interesting. So the way they've defined it, broadcast module sends whatever pulse it received to all its destination modules. But when they say what the button does, a low pulse is sent to the broadcaster module. That suggests to me either part 2 will have us send different signals to the broadcaster, or we have some recursion here and some of these modules actually send signals back to the broadcaster. That might happen. I haven't analyzed the topology of this. So anyway, so we put broadcaster signal low. Sender is none. Right. Should we just, instead of sending self, which is a bit awkward, let's just send self.name, because that's the only thing we ever use. And then when we pull out the name, let's say sender. Yeah, that makes more sense. So sender is just a string, not a module. It's just easier to pass around. So then we pass our names, and this one gets the name out. Yeah, okay. All right, so broadcaster false. None, because broadcaster won't use a sender anyway, so nobody sent this signal. Okay, so we put that one signal out, and then while Q module, so we need to take the thing, take something out of the queue. So it's going to be module pulse value sender equals q dot get. So we take something out of the queue, and then we want to actually process that. So we want to say module dot pulse with this given value and this given sender. So that will then put stuff on the queue to be processed later, but we won't do that yet. We'll then take what's next on the queue. Okay, so the queue should use FIFO ordering. All right, so is that okay so far? Okay. That's everything defined. Now what do we actually do? I think we've just pressed the button 1,000 times, right? After pushing the button 1,000 times, okay, so let's see if we can actually push the button 1,000 times without it crashing. All right, just run it. How long does it take? Still running. I'm worried. Should I print I? How slow is this thing? We're running 1,000. It's stuck on 0. Of course it is, because you don't say while Q, you say while not Q.empty. Q is always going to exist, so that's an infinite loop there. While not Q.empty. Right, go. There we go. It's quit. Good. So we press the button 1,000 times. What do we want? We want to accumulate all the low pulses and the high pulses. Okay, so low pulses equals 0, high pulses equals 0. So every time we take from the queue, if pulse value is high, high pulses plus equal 1, else low pulses plus equal 1. Okay, we need to make these global. Okay. And then multiply them together, and that's it. That big number. Wrong. Of course it's wrong. I'm always wrong first time. Okay. Oh! Thanks for the raid, Stew Squared. Welcome in. Were you just doing this problem? You just finished. Nice. It's, I mean, I've only just finished putting together all the module definitions and stuff, and I just got the wrong answer. But now to actually decode this, all right, we'll try the try the example then. All right, so what's the example they've given? That. All right. So in this example, the same thing happens every time. So we can just check that one button push matches this sequence, I guess. So Stu squared, what language were you using? All right, so just switch to my. So that's this input. So you're using Scala. Nice. 32. 32 is... Well, that's correct. 32 is correct. And try 1,000. I don't like it when it's correct. 32 million. That is spot on. Alright, well, fine. Let's try the second example then. So that's the one with independence. Every press, it's a fresh state. So the second example, we have oh, I know what the problem might be. Aha. Now I realize why there was a weird... Okay, let's use the second example. I think this might actually find our problem. Okay, so we've got con. No, okay, we've got this thing called output, which has no definition. So it's a mysterious module. We don't know its type. It doesn't do anything. So foolishly, I disregarded it. But actually it matters because you still need to count that pulse. Yes, that was my mistake. Okay, so it doesn't do anything. Should we just call it a... So either I just create a new type called unknown type, and when it receives a pulse it does nothing, or I can just make it a broadcaster, but just leave its outputs empty, so it's kind of not doing anything by default. We could do that. Alright, let's say if output not in module table. Alright, so if it's something we've never seen before, I want to create a module which is just a broadcaster module. So we'll say module table for this output is going to be fresh broadcaster module of type broadcaster. And because it has no definition, then that's safe, because it will just have an empty list and it won't send any other pulses, but it will receive a pulse. And yeah, okay, if we now run this on the test example, let's see what we get. 1168750. 1168750. Okay, it's correct on that example. Go back to the previous example. $32 million. All right. Big example. We've got that number now. That was a trap that I fell into. It's taking a while. Okay, good. Yeah, that was. I shouldn't have cut that corner. Like, I was like, this module doesn't do anything. Let's just discard it, pretend it never existed. That was bad. Of course, it has a purpose. He wouldn't put it in the input if it didn't have a purpose. I shouldn't have dismissed it. Okay, here comes the fun part. Oh no. Part 2. Let me guess, it's going to be something with some major loop which counts, which maybe is some sort of binary counter or something which counts to billions. Alright, let's have a look. Part 2. The final machine responsible for moving the sand down to Island has a module attached named RX. The machine turns on when a single low pulse is sent to RX. So that was the thing we discarded. Okay. Reset all modules to their default states. Okay. Waiting for all pulses to be fully handled after each button press. What is the fewest number of button presses required to deliver a single low pulse to the module named RX? Alright, I have a bad feeling that we're going to have to actually work out the semantic meaning of these pulses, and I mean, nevertheless, I can try running it. So let's just try running it then. So that was part 1. Okay. Part 2. I suppose we want to just while true. We're gonna need to keep track of the pulses. Alright, so let's do 4 presses in count. So this counts from 1, right? Yeah, I think so. So for presses in count, so it counts infinitely. Press button. Alright, and then when do we stop? Single low pulse to the module named RX. Okay. So we just need to see when any signal. Okay, so if the pulse, if we have received the pulse as the broadcaster, whose name is RX, then we're going to have to Okay. Okay, so the special exception here. If self.name is Rx, also, yeah, okay, that's fine. Did I give it the right name? Why did I... Oh, that's... Okay, it works, but that's wrong logic. It should be called output, not broadcaster. But we don't index it by the name, so that's fine. But yeah, I've given it the wrong name. Okay, now it's got the right name. The program for part 1 would still work, but yeah, the name was wrong. Alright, if self.name equals Rx and not value, so the pulse is low. Print, so just print something. Rx has been received a low, because the thing is, this is all part of one big queue. So it could be that Rx receives a low, but then it receives a high in the same button press, and then we'll miss it. So let's just make sure we're printing it so we catch it when it happens. Now, if this happens, then we just want to stop everything else, don't we? We don't want to... We don't want to continue pulling off the queue, even though it says waiting for all pulses to be fully handled after each button press. The important point of this is fewest number of button presses required to deliver a single low pulse to the module named Rx. What do they mean by single? They just mean the first low pulse. Like, what if you press the button and 2 low pulses are sent to Rx? They don't mean when it says single low pulse. No, I think it just means the first time it ever receives a low pulse. The word single is a bit misleading, maybe, I don't know. Okay, so let's just say the first time it ever receives a low. Let's just do queue.clear, clear the queue. Well, is that just a hack? Is that just a helpful hack that will, no, that's not how you clear a queue. Queue dot put empty, get queue size, queue, all tasks done, full. Isn't there a way to just clear the queue so that we don't want any more tasks to be done? I don't think there is. I guess because of parallelization and stuff, you're not allowed to do that. Makes sense. Yeah. Okay, fine. In that case, we just have to globalize a signal, don't we? We just have to say Rx equals false. Make that a global variable. Rx equals true. Return. We don't want to add anything else to the queue, just because there's no point. And then in this logic here, where we're actually pressing the button, while not queue.empty. Queue.get if those. Oh wait! I'm doing this wrong. It doesn't need to be done at the module level. Get rid of this. It's far simpler than that. We just don't process the pulse in the first place, because we're doing it here. Right, so if module.name is Rx and pulse value and not pulse value, break. How are we going to do this? Should we just say press button will return a boolean? So we actually return true if that happens. And if anything else happens, we return false. And here we're just saying if press button print presses. That's how many presses we did. And then break. Alright. It's gonna be an infinite loop, isn't it? If presses percent 1,000, let's say 10,000 is 0, print presses. This is gonna go on forever. I should just leave it running for a while just in case, but clearly it's a there's more to it than this. Alright, so we've got to actually figure out what's happening to Rx. Rx is mapped to by KL. My guess is that he's created some sort of counter. Want to know the order of magnitude of the answer? Yeah, okay, you can tell me, because I'm guessing it's too big anyway. So, this is not gonna execute. So, yeah, I'm guessing it's some sort of he's created some sort of counter out of these, and so, for example, like. Gotta look at the ands because they are the conditional ones. Mine was a 15-digit decimal number. That's, yeah, in the quadrillions. Interesting. Alright, there's no point running this. We know that it's gonna take a long time. So how do we go about this? Either we try to spot patterns in the So there are sections of this that could be discarded, maybe, if they're not We need, you know what we need? We need a diagram. Could we use GraphViz here? I mean, it's already almost in the format of GraphViz, isn't it? It's just the and thing. Actually, it's pretty much the perfect format for GraphViz. It's just that we want TS here to be the same as... Yeah, but we can fiddle with that to make it work. So if we plug this into GraphViz, we'll look at the diagram to see what the heck is going on. I don't have GraphViz installed. Let's see. Can I get GraphViz in PyCharm? Okay, let me fiddle with the modules here. Project properties. How do I... Where is... Oh my god, okay. File settings. Project settings. Plugins? No, not plugins. Project interpreter. Here we go. Off is let's install GraphViz. Okay. It's installing. Okay, it's installed. All right. So we want to make a graph. I don't remember how to do this. Let's have a look at graph is Python. Sure. We're only trying to do very basic things here. Just add an edge. We want different shape depending on what type of node it is. So like, okay. Graph is documentation. This is good to remember because in the future I might want to use GraphViz. For this stuff, create a graph object. All right, so input GraphViz dot equals GraphViz dot digraph. Do we want digraph? Yes, it's directed. Okay. Alright, so let's try this. Man, I'm hungry. This is gonna take me a while. We don't need RX anymore, take that out. Dot equals GraphViz.digraph. Alright, so what do we do? Add nodes and edges. Dot. Okay, so the moment we create a module, let's just do dot node with my name. So that creates a node. I would like a bit more than that. We want some attributes here, node attributes. I've got to have a look at the documentation to know what attributes we can use. There's constraint. So I want shape. Here we go, attributes. Shape equals, okay, so we've got shape. What shapes do we have? There's point. I just want to list, okay, box. All right, should we say we use box for hang on. So I don't know, use box for, okay, so if m type equals shape table equals, just define this up here. So it's going to be broadcaster. What shape should we have the broadcaster? But I still can't find it, just a list of shapes. All right, I don't know. Use the default ellipse for okay, here we go. Styling. No. Why is it so hard to just give me a list of all the shapes? Oh, okay, I'm gonna have to Google this, aren't I? Graph, viz, node, shapes. This isn't just an aesthetic thing. I just want to know. Oh, okay, here we go. Node shapes. All right. Whoa, lots of shapes. There are a lot of shapes. Okay, so let's say doesn't really matter what we use. Okay, so let's say just use star for broadcaster. Fine, just use a star. What was the other one? Flip, flop, or We can use box for that. And conjunction, we can use... Do they call it ellipse? Yeah, ellipse. What's the difference between ellipse and oval? I guess they are mathematically different shapes. Ellipse is defined by having 2 focal points, and oval is, I guess, a circle that's been physically stretched. They're not the same thing, are they? I don't think so. Do I want oval or ellipse? Let's just go with ellipse. Okay, so we want shape equals shape table name. Okay, can I just print dot as is right now? Okay, let me... That's part 2, by the way. Dot, dot. Alright, how do I visualize it? Render, use dot dot render. Graph is dot graph. Hang on, so we want format equals ping, should we say? And then we want dot dot render Wait, will it just create a ping file in the same directory? No. Yeah, try it. Dot dot node given name shape table. No, not shape table name, damn it. Shape table then type. What's happened? Windows path dot. Hang on, I need to give a actual location, don't I? Directory equals can I not just dump it here? Make sure the graph is executables are on your system's path. Is that the problem? Hang on, can I not just say, okay, test? We've got a directory appeared called test. And that's its definition. Okay, that seems... Okay, this is taking me a long time, but I mean, once I get the hang of this, I can use graphics in future. Alright, I think the problem then is okay, we don't need that. We can just dump it here, but Okay, fine. Windows path dot. Make sure the graph is executables on your system's path. Wonderful. We're gonna have to fiddle around with. I think we can just download for Windows, can't we? Download 9.0 for 64-bit installer. Yes, add graph is to the system path. Okay, we've installed GraphViz in Windows. Now I'll try it. Alright, do I maybe need to... I don't know, close the IDE or something and open it up again? I might have to go have dinner. This might be the first time I don't finish in one session. Because there's stuff I want to do. I want to make this graph work. I just want to see what we're dealing with. Right, try running it. There we go. Where's the... Okay. Now, just add the edges. So whenever we added output, so okay, for output and right.split, we have node, so it's dot edge tail name and head name. So is it just tail is where it came from? So it's gonna be, is it? So it's gonna be M dot name output dot name. Oh, no, in this case it would be output. Let's try that. Alright. Ooh, got something. Wow, look at that. All right, now, how do we interpret this? Can I not zoom in here? I can, but then it's not got good. can't auto scroll. All right, so my first question really is there any major thing we can just cut out of this whole graph? Because we know it won't affect our x. Looks like the answer would be no, probably. No, okay, because look, this all affects GV. Ah, but there's an interesting pattern here. That's very interesting. So it would be like, if I'm understanding that, it'll be essentially what we have here is like a binary counter, isn't it? So this is going to alternate between 0 and 1, 0 and 1. So will each of these. And it's waiting for all of these to give 1. And as soon as that happens, it outputs 0. But it's also sent to xt, but it also sends stuff to kx and to, so it actually flips those bits, kx, tz, and gz, which is irregular. That means it's not. That's strange. Okay, fine. That's a thing. But that's a compartment that does something. So ultimately, it'll take a certain number of steps until xt is triggered. Xt is an AND gate in itself, and it has only one input. So is it just there's no point to it really? Okay, fine. So if we can keep track of when xt gets triggered. Now this sequence doesn't reset perfectly because then it sends a signal here and here and here and then no here to tz. So then the next, yeah, whatever. I don't know. Something interesting is going on there, but we wanted to keep track of when xt gets triggered. All right, what else is going on? MK. We've got another one of these. Is it isomorphic? Because if it's isomorphic, then we can cut out one of these, can't we? If this whole subgraph on the right has the same properties, edges, as the subgraph in the middle, then it doesn't actually matter what's going on. We can just delete the one whole lot, can't we? And just have xt have two edges going into KL. What about on the left here? It looks like it's similar. I feel like it. Oh. All right. So from this, I would say what we're interested in is when do xt, mk, zc, and fp get triggered? Because if I can find the period, if there's a pattern to them, So Rx will get triggered when these four, it's basically waiting for these four numbers, XT, MK, ZC, and FP, to all be high, right? And XT is... So basically, these are counters. These are each separate counters, and I think the nature of these edges have caused them to be counting to a certain number, but also reset in a weird way. It doesn't reset. It flips. So here it's flipping JZ and LF upon triggering. I'm not sure what I can do other than just analyze XT. Let's just start somewhere. Let's start with XT. I want to know when XT goes high. So we want to know when there's a signal, when there's a high into XT. And what the pattern is. Alright. XT then. So that was really useful. Graph. So we want... yeah, we don't need to do that. Alright, so we don't really need to do this if press button thing. So we press button. If yeah, just press button infinitely, whatever. Whenever we don't need to worry about this RX thing anymore. It's not gonna happen. How do I... Alright, tell you what, let's just pass the count as a parameter. This is a bit of a hacky way of doing this. Press button, presses. Just so I can print the count. Okay, so we send the pulse. We want to check when we have received a high to XT, MK, ZC, or FP, right? So if module.name in, so it's going to be XT, MK, ZC. This may well be the toughest problem yet. You cannot just write, because you can do any, this system can do anything, so you can't just write code that will solve this problem. You kind of have to take this apart and look at things with your own eyes. I don't think you could just write generic code which would work out when RX. And nor could ChatGPT, I bet. If Module.name in that. Print. Module.name. Count. Alright, let's just do that for now. I can't see what I'm printing. Stop. Let's just go back to this. Alright, so... Hey. 2291, 2291. Oh, interesting. This is all happening within one button. Oh, so it's even more complicated because these guys can turn on. Within the same button press, they can turn off again. If so, GV sends a high. What's going on here? What am I trying? I don't. Not sure what I'm supposed to do with this information. Alright, so let's just look at. Oh, does it happen every button press? Oh no, it's supposed to. Oh no, these are zeros. We need it only. We need it to be and false value. We need it to be a high specifically. All right, try that now. I was counting all the lows. All right, so now it's still getting lots of highs. So here we got 1, 1, 1, 1 on all on the same button press. So why wouldn't that trigger? Because it kind of matters when it happens. It's not just about which button press, because they can go on and off. Alright. Let me see what the actual value being sent is, in what order. So they only ever sent ones. Oh, wait. Hang on. Okay. I'm reading this wrong. For Rx to be triggered, we're waiting for Rx to receive a low. Okay. That means KL has to receive has to be holding a high from all 4 of these, right? That's what it means for the conjunction. yeah, for Rx to receive a low, we need KL to remember a high on all inputs. Then it sends a low. Otherwise, it sends a high. So we need all inputs to be high to send a high. And we need, basically we need, yeah, okay. So these 4 things are flip-flops. Ah, of course. So I don't care about what their input is. Input just causes them to flip. We only care about what their output is, because it's flip-flopping. So, oh god. Fine. Print module name.count. Okay, so we actually need to know what value they're outputting then. Not module dot flip state. Right, I want to see what they're outputting. Let's try that now. Wait, what? Always true? No. Module dot flip state. No, it's supposed to be flipping. Huh? Hang on, have I understood flip state correctly? If it receives a high, it does nothing. Oh yeah, of course. If it's a low, it flips between on and off. And outputs. Ah, so we want to see when they receive a low. Not a high. I'm getting these all mixed up. So if module and not pulse value, print. Just do that for now. Okay, that's interesting. Okay, now we're getting some better numbers here. So, and we just say not, so int not module dot flip state. I want to see what they will output when that gets executed. No. Huh? Okay, so module is receiving a low. When you receive a low, you flip between on and off. So why isn't flip state flipping? Every time it receives a low, it should flip, shouldn't it? What's causing... Why am I only seeing ones here? Flip state, every time we see this happen, it should flip? I don't understand. So, for example, let me just focus on XT then, alright? XT receives a low. Whenever this happens, we print the name, the count we're on, and I want to see what the opposite of the flip state is, because that's what is going to be outputted when this pulse value is low, and that flips it as well, right? So why is it always 1? I don't understand. Isn't it supposed to go 1 0 1 0 1 0 1 0? But we can see a pattern here, so now it's really just a case of doing some okay, look, it's every 4007, isn't it? That's the pattern. But I don't understand why we're not seeing a 0. Alright, well, if it's outputting a 1... What causes the flip state to go back to 0? Another pulse value of low, surely. But if that were to happen, wouldn't we see it? Oh, I've got... Alright, I don't really understand. Anyway, we found out that it's at 4007. Let's just assume this is going to get us the answer. So 4007. Let's just make a note of these. Is it consistent? It looks like it is. Alright. Let's try MK. Three nine three one. Okay. So is it just going to be the LCM of these? But is it going to be? Yeah, that it would just be that, wouldn't it? And then ZC. So this is basically a manual. We're doing manual work here. You could program this, make some automated script, but then you'd have to look at the inputs to the. You have to find. Yeah, I think today we'll just do some manual stuff and just leave it at that. Forget about trying to write generic code. Alright, so then we've got ZC. Did I not? 3923, okay. Alright, I don't think there's much more to do after this. I think that will just give us the answer. Unless I don't think he's thrown in any other tricks, because that would just make it really, really brutal. I assume this is just a repeating period. 3 7 6 7. I don't understand why these are all 1s. That's very strange to me. Maybe I've done something wrong somewhere, but 3 7 6 7. But these are quite nice numbers, so... There? Is that the answer? If it's wrong, then I don't know how the heck I'm gonna debug this. Okay, wow, that's right. Bloody hell. So Stu Squared said their number was a 15-digit decimal number. Well, mine is 15, yeah. Okay. That really showcased the beauty of GraphViz. Well, GraphViz not only prints your graph, but it does lots of really smart stuff behind the scene to make it. It's kind of like trying to minimize the amount of crossing with the edges, and in doing that, you can sort of see the isolated kind of like the subgraphs, which is especially useful for directed graphs. So here you can see what's going on. You've basically got 4 counters. They're each counting to a different prime. I assume it's prime. It looks like it. And that prime is defined by the way that these counters these edges are thrown back to LF and JT. That basically, I'm not interested in going into it fully. You could, but by running it and seeing when MK, XT, ZC, and KQ, FP are triggered, you can work out when each of these are high. And so all 4 will be high simultaneously at the LCM of those 4 numbers. But everything comes from the graph. You need the graph. So at least I figured out GraphViz. It took a while, but now I can use that in future. There's definitely some problems in the this year that would have made use of GraphViz. I just never really sat down and did that. Yeah, I guess I'll just output my code as is. Because not more I can do there. I'll leave, yeah, I'll sort that out later. Like, I'm trying to put my code into a nice state that people can learn from, but in this case, I kind of need to make a comment, just say, yeah, I kind of did this manually. Or at least a mix of manual and automation, but we'll sort it out. Alright, so that took me 2.5 hours, not too bad. So that was a tough problem. Some might say that was the toughest problem because you could not just solve it with automation. You actually had to delve into semantic meaning of the graph and what's actually going on. That's not easy. But it was a very good problem. That might have been one of the most cleverly devised problems of this year. Leaderboard 20. 15 minutes 52. That's quite high. But still quite impressive. 10 minutes 26. 15 minutes 52. Yeah, I mean, if you could decode all that and figure out what is good. Okay, if you could just plug everything into GraphViz, and if you're smart with these problems, plug everything into GraphViz, which you can do because it's almost in the correct format. Like the input they've given you is almost looks like a GraphViz script. So if you to plug it straight into GraphViz and then just look at GraphViz, I think you could make a wild guess and say, okay, those 4 things before there, maybe you want to check what their period is. So, and then just get the LCM of those numbers. I think, yeah, 15 minutes. I think you could make some smart estimations there. Bit of guesswork, bit of, but it's not really guesswork. It's just like smart guessing because you know what kind of things Eric is going to throw in there. It often involves the LCM, so yeah, I can believe that. let's look at my private leaderboard then. Just me and Sam so far. Marrow, good work there, catching up. Let's check out Captain Coda. Oh, he might be coding now. He might be streaming now even. Alright, we got 3 people have done it. Alka is working on it. I guess he's also streaming. Captain Coda, I believe, is behind because yesterday he didn't... Oh no, he did do yesterday's problem. Offline, I guess. Okay. Fun stuff. Stats. I have a feeling that might stay quite low, because that's not easy for anyone to solve. Alright. Alright, that was a really nice problem, though. So, I would say one of the best problems we've had. Yesterday's was a good one as well, I think. But they were very different. One was quite textbooky, the other was quite original. Today's was quite original, so...
Confused is in between here. Because on the flip-flop...
Alright, Captain Coda is indeed streaming, so I guess... Do I even have enough people for a raid? We've got a few people in here. Yeah, let's do it then. Let's raid Captain Coda. I have been enjoying the Captain Coda's streams. He is an educator. He teaches students online in this stuff, so he has a good style for people to learn from if you want to learn more about append code. So I'm just gonna do that. All right, and yeah, I gotta get to the processing of the YouTube video and everything. All right, see you tomorrow. If I have time. I have a flight tomorrow. We'll see. I might even do an airport stream. Nah, I don't think I can do that. I won't have my webcam in my backpack. All right, see you, Wugga. I don't know how much of that you understood. That was probably the problem which is the most technically demanding in terms of technical knowledge. All right, well, some of these days are quite intuitive. Sometimes it's even like code like a basic Dungeons and Dragons, you know, battle system or something, because I know Eric is a fan of Dungeons and Dragons himself, the guy who makes these problems. So sometimes it's intuitive, sometimes it's really academic. All right, the Captain Coda is a fun guy. He's going to be tackling this problem now as we speak. So, yeah, see you guys tomorrow.